So as another application of the Lagrange formalism that's really going to take advantage of this whole concept of a generalized coordinate is we can apply this to the analysis of an electric circuit. So I've drawn here just a very simple circuit with a battery, an inductor, a resistor, and a capacitor. And we first will just analyze the energy that we can assign to each of these devices. So if we look at an inductor, it has an energy of 1/2 L, the inductance, times the current squared. So I'm going to use the little I for the current. I look at a capacitor, and it also stores energy of 1/2 Q squared over C. We look at a battery, and the battery provides energy given by the voltage across the battery, this E times the amount of charge that moved across the battery. And finally, we have the resistor. And the resistor dissipates energy. So we know that it has a power of I squared R. So this is the power. So when we go to look at the energy that it dissipates, it's actually just I times R. So we have these terms, and we can then analyze these in terms of what we're familiar with. So this inductor, it looks like a kinetic energy term. So I'm going to rewrite this as a 1/2 L Q dot squared. The capacitor looks like a potential. So this looks very similar to a spring. And so that potential is 1/2 Q squared over C. The battery, this also looks like a potential term, but it's like a gravitational potential. So it goes as minus Q times E. And finally, this resistor is like our non-conservative force because it dissipates energy, and we would assign that Q to be minus Q dot times R. So there's a direct analogy between the components of a circuit and a mechanical system. And in fact, this is a common practice that you can model mechanical systems with electrical circuits. So engineers do this all the time. So I can write a Lagrangian then, just by the normal way of T minus U. So my Lagrangian for the circuit is 1/2 L Q dot squared, then minus 1/2C Q squared plus Q epsilon, and my Lagrange equations, d by dt, di L by di Q dot minus di L by di Q. And then I have the term minus the Q non-conservative. So when I do this, I take first my partial with respect to the current, and I'll end up with an LQ double dot from this term. and then minus di L by di Q. So that gets me a Q over C. I have a minus here, but I need a minus there, so that's a plus. Minus di L by di Q, so that would give me a minus epsilon, and then finally a plus. My generalized force is a Q dot R equal to 0. And so this becomes a differential equation in the charge Q that I could solve.